Okay, so now that we've discussed how to calculate a determinant, let's turn to the issue of figuring out what determinants are actually good for. So what we're going to find here, or for us, what we're going to find is that determinants are actually useful for finding a formula for the inverse of a matrix and can be used to help us solve systems of equations in certain scenarios. So let's start by defining two matrices that relate to the matrix that we start with A. So remember, if we start with an n by n matrix, there are n squared entries in that matrix, and each one of those entries corresponds to a cofactor. So we can define the cofactor matrix of a matrix A as the matrix that organizes all of those cofactors. So the ij entry inside of the cofactor matrix is the ij cofactor of that matrix. And oddly enough, it turns out that the cofactor matrix is useful, but it's actually its transpose that is more widely used. And its transpose is defined as the adjugate matrix. So the adjugate matrix of A is defined as the transpose of the cofactor matrix. So the ij entry in the adjugate of A is equal to the ji cofactor of the matrix A. So here we have the same piece of data just represented as it's transposed here. So let's see what these things look like for an ordinary 2x2 matrix. So for an arbitrary 2x2 matrix, we should have four cofactors. So the 1, 1 cofactor should be -1 to the 1 plus 1 multiplied by the 1, 1 minor of that matrix, which is just the number d. So the 1, 1 cofactor is just the number d, which is the bottom right-hand corner of the 2x2 matrix. For the 1, 2 cofactor, we should be looking at -1 to the 1 plus 2. We then delete the first row, second column, and end up with just the number c, which is the number in the bottom left-hand corner of our 2x2 matrix. And so the 1, 2 cofactor ends up equaling -c. The 2, 1 cofactor is -1 to the 2 plus 1, which is equal to -1, multiplied by the determinant of whatever's left over when we delete the second row, first column, which is just the number b, the upper right-hand corner of the 2x2. So the 2, 1 cofactor is equal to -b. And the 2, 2 cofactor is -1 to the 2 plus 2, which is equal to 1. And then we multiply by the 2, 2 minor, which is obtained by just plugging out the number left over when we delete the second row, second column of our 2x2 matrix. So we end up with just the number a, which is the upper left-hand corner of the matrix. So if we put all this information together in the order that we calculated everything in, we get the cofactor matrix. So the cofactor matrix of an ordinary 2x2, or of a general 2x2 matrix, should have rows equal to d, -c, -b, a, where the original rows of the matrix were a, b, c, d. So d, -c, -b, a. The adjugate of this matrix, of the original matrix, should be the transpose of the cofactor matrix. So the adjugate of should be the matrix whose rows are d, -b, -c, a. So what is the adjugate good for? So if it's worthy of a name, why do we care about it? Well, let's just look at our 2x2 example. In our 2x2 example we just calculated, we found that the general adjugate of a 2x2A, where the rows are the numbers A, B, C, D, is the matrix whose rows are D, -B, -C, A. And here's something interesting. It turns out that when we take A and multiply by its adjugate on the right, we produce a new 2x2 matrix. And one thing to note about this new 2x2 is that it has zeros on the non-diagonal entries. So this is a diagonal matrix. And when we look closely at the diagonal entries, we realize they're both the same, and they're equal to the number AD minus BC. And what we found earlier is that for a 2x2 matrix whose rows are A, B, C, D, the determinant is A times D minus B times C. So by taking A and multiplying by the adjugate on the right, we end up producing the determinant of the original matrix multiplied by the 2x2 identity matrix. And it turns out this formula generalizes to a matrix of any size. So our major theorem about adjugates says that if we take any square matrix and multiply by the adjugate on the right, that's the same thing as taking our matrix and multiplying by the adjugate on the left. And the result is always the determinant of our matrix multiplied by the identity matrix. And if we start this formula for a moment, we might realize that there could be some utility here. Remember the notion of a non-singular matrix. A non-singular matrix is a matrix that has an inverse. And inverses have the property that when we multiply a matrix by its inverse, we produce the identity matrix. Well, if we look at the formula that we have here, we realize that we can isolate the identity matrix on the right-hand side of this equality by dividing everything through by the determinant of A. What we would then end up with is a formula that says A multiplied by adjugate divided by determinant is the same thing as adjugate divided by determinant times A, which equals the identity matrix. This suggests that we can use adjugates to define a formula for the inverse of any matrix. So we can state that as part of our theorem. If A is non-singular, well, that should be the same thing as saying that the determinant is not zero, so we can divide by it in this formula. So the property of being non-singular is the same thing as the property of having a non-zero determinant. And furthermore, once we know our determinant is not zero, we know that the inverse of our matrix has to be 1 divided by the determinant multiplied by the adjugate of our matrix. So the upshot here is that if we can calculate the determinant of our matrix, we can immediately infer whether or not our matrix is non-singular. A non-zero determinant tells us that the matrix is non-singular and therefore has an inverse. And if our matrix has zero determinant, that means that the matrix is singular, which means that it does not have an inverse. So that sounds great, but we should always keep in mind that a determinant calculation is a non-trivial calculation. There's a lot of effort that goes into calculating a determinant. And the most efficient way to do it is to use our LU algorithm, so to row reduce our matrix to upper triangular. But the issue with that is by doing all of that work, we end up figuring out the rank of our matrix anyway, which tells us whether or not we're non-singular. So determinants are not the most efficient tool for figuring out whether or not a matrix is non-singular. Rank is actually a better tool here. Also, we run into the same issue when calculating an inverse. Previously, we saw an algorithm for calculating the inverse of a matrix where we took our matrix, augmented with an identity, and did row reductions. This theorem is suggesting an alternative way to find our inverse, but we should be a bit wary of this formula. Consider the effort that would go into calculating the inverse of a matrix using this adjugate formula. To calculate the adjugate, we need to transpose the cofactor matrix. And to calculate the cofactor matrix, we have to compute n squared n minus 1 by n minus 1 determinants. And that's a lot of effort. So if we tried to use this formula for like a 5 by 5 determinant, we would have to calculate 25 4 by 4 determinants and then divide by the original 5 by 5 determinant. And that's a lot of calculation. So this is a theorem that is true and it works, but it's not necessarily computationally attractive. But it does offer some nice formulas for smaller matrices. So one upshot here is we can use the formula for the inverse of a matrix in terms of its adjugate for a 2 by 2 matrix, and we get a relatively simple closed formula for the inverse of a 2 by 2. So if our original 2 by 2 matrix has rows A, B, C, D, the adjugate formula for inverses says the inverse of that matrix should be 1 over the determinant multiplied by the adjugate of that matrix. And remember the determinant of a 2 by 2 whose rows are A, B, C, D is A times D minus B times C. And then the adjugate of a general 2 by 2 with those rows has rows D, negative B, negative C, A. So if AD minus BC is non-zero, we know our 2 by 2 is invertible. And under that condition, we have a closed formula for the inverse. 1 divided by the determinant multiplied by the adjugate. A lot of people remember this 2 by 2 formula by switching the two diagonal entries, A and D, and then negating the other two entries. So B becomes negative B, and C becomes negative C. So this is nice to use for 2 by 2s. So in this equation, what we're looking at is a 2 by 2 matrix whose rows are 1, negative 3, 7, 4. The determinant of this matrix should be 4 minus a negative 21, so plus 21. So this matrix has determinant 25. 25 is not 0, which tells us this matrix is invertible. And our formula for inverses says that the inverse of this matrix should be 1 divided by the determinant, so 1 over 25. Then we multiply by the adjugate, and for a 2 by 2, that's obtained by swapping the two diagonal entries. So 1 and 4 are switched here. And then we negate the other entries. Negative 3 becomes 3, and 7 becomes negative 7. So we can quickly invert our 2 by 2 matrix by taking advantage of this adjugate formula. Another calculation to look at is here we're looking at a 2 by 2 matrix, but this matrix has the property that its determinant is 0. So 13 times 12 is the same thing as 39 times 4. Once we know the determinant of this matrix is 0, we know immediately that this matrix cannot have an inverse because we can't divide by the determinant in the formula for inverses. So this matrix has to be singular. Singular means does not have an inverse. Okay, so finally, let's conclude this lecture on determinants with an application that one can actually use, and that is Kramer's rule. So Kramer's rule takes advantage of the adjugate formula for inverses of matrices and the fact that inverses can be used to solve systems of equations when the matrix does have an inverse. So here's the statement of what's called Kramer's rule. Let's say that we know we are studying an invertible matrix A. Then let's say that we're studying a system of the form AX equals B. It turns out that each of the coordinates of the one solution to this system, X, can be calculated by only using determinants. So the vector X that solves this system is guaranteed to equal 1 divided by the determinant of A multiplied by this vector of determinants, where the first entry is the determinant of a new matrix A1, the second entry is the determinant of a new matrix A2, and then we keep going until we get to the determinant of this last new matrix AN. And the ith matrix in this vector of determinants is obtained by replacing the ith original column of A with the vector B in question. So this theorem, in addition to giving us a formula for X, is also telling us how to calculate each of the individual entries. So if for whatever reason you were studying the system AX equals B and you wanted to know the second entry of the solution vector and you didn't care about the other entries, you could look up that solution or that position in the solution by taking the determinant of the matrix obtained, by replacing the second column of A with the vector B, and then dividing by the determinant of A. So let's see this in an application. So here we have a perfectly good system of 3 equations with 3 variables. This system of equations takes the form AX equals B, where A organizes all of the coefficients of the variables in the system. The vector X is organizing all of the variables in the system. So here the vector X is the vector X, Y, Z. And the vector B is organizing all of the constants to the right of the equal sign in this system. So here the vector B is the vector -2, -88, -9. So let's say that we wanted to use Kramer's rule to solve the system. Well, to use Kramer's rule, the first ingredient we would need would be the determinant of the coefficient matrix. Because knowing that determinant will tell us whether or not the rule even applies. Because if the matrix has a 0 determinant, we can't even use the rule because that matrix would be singular. For this example, if you calculate the determinant, you end up producing the number -9. So once we know the determinant of this coefficient matrix is -9, we know that this matrix is non-singular because that's a non-zero determinant, which means that we can apply Kramer's rule. So to complete Kramer's rule, we need to calculate the determinant of 3 new matrices. We want to take this matrix A and then replace each one of the columns by the vector B and take resulting determinants. So the first matrix to look at is the matrix A sub 1. A sub 1 is obtained by ripping out the first column of A and replacing it with the vector B and then taking a determinant. When we do the work here, we end up with the number 351. To calculate A2, we need to rip out the second original column of A and replace it with the vector B and take a determinant of the resulting new matrix. When we do the work here, we end up with the number 372. Finally, for the third new matrix, we rip out the third column of the original A and then replace it with the vector B we're working with. And then we take a determinant of what's left over, and when we do that calculation, we get the number negative 60. So Kramer's rule says we can use the data in this sequence of 4 determinants to figure out the unique solution to AX equals B. According to the theorem, the system AX equals B is solved by the vector x, which is equal to 1 divided by the determinant of A, so that's negative 1/9. And then we multiply by the vector organizing the determinants of A1, A2, A3. That vector is 351, 372, negative 60. So in this system, x is equal to 351 divided by negative 9. The y in this system is equal to 372 divided by negative 9, and z is negative 60 divided by negative 9. So Kramer's rule gives us a method for solving systems of equations where the coefficient matrix is non-singular, and we only need to use determinants here. But again, the upshot is that we don't need any row reductions here if we're happy to do these determinants by hand without row reductions. But the downshot is this is not necessarily the most efficient way to approach the problem because, or the general problem of solving systems of equations. Because for one, this only works if the coefficient matrix is non-singular, and in addition to that, even if the matrix is non-singular, calculating these determinants in any reasonable amount of time would involve some row reductions anyway. So once again, we encounter the issue that it's hard to avoid row reductions completely when working with matrices.